Here are some solutions to the worksheet on section 2.1, so you can compare this to results that you got in class. I'm just going to sketch the results here so you can just check answers. Remember our steps are to first compute f prime, and so in this case f prime of x will be 3x squared minus 6x, and we set that equal to 0 and find out that that happens when x is 0 or when x is 2. So we're going to put our marks on our number line at 0 and 2. So this is those are called our critical values, and they're just called critical values because they're important. So critical in the sense of being important. So these are our important values of x, and then we want to sample something over here, so probably -1 would be a good point to sample. We want to sample something in here, so x equals 1 would be going to sample. And we want to sample something out here, so x equals 3, say, would be a good one to sample. If we do that, we'll find a positive answer here, a negative answer here, and a positive answer here. So we know that this is always positive, always negative in between. Again, the way I'm determining that is I'm putting those numbers into my f prime formula. So f prime of -1 is 3 times -1 squared minus 6 times -1. So that's how I'm getting, which is a positive number. It's actually 9, but all I care about is that it's positive. So that's how I'm getting that this is positive. And similarly, I'm putting 1 in for x to get this and this. So the key here is that the number line is telling us the sign of f prime of x. That's what we're plotting across here: positive, negative, positive. And so what that means is that my function, my graph of f, my function f, is increasing on the intervals -infinity that's hard to make, -infinity to 0 and 3 to infinity. So those are the values of x where I have positive slope, which means I have an increasing function, and then my function is decreasing in between 0, I'm sorry, not 3, sorry, 2, right, starting here. So so f will be decreasing in between 0 and 2. So same process for the next one. Let me just write down the answers. So here the derivative you get should be 9x squared minus 4x cubed. And so when you set that equal to 0, again, you're going to factor that. You can factor out an x squared, and you'll have 9x minus 4 left inside. Oops, not 9x minus 4. Sorry, 9. Well, now I can't erase it. All right, so maybe I can undo. Nope, stuck with it. Anyway, when you factor out x squared, you'll have 9 minus 4x left. So again, I'll put my 0 and my 9/4 on my number line, and I'll be able to sample some points, and I'll find that my derivative f prime of x is positive out here left of 0, then it's positive some more in here, so I could sample like -1 and 1 to find that out. And then when you get to the right of 9/4, I'll have negative slopes. So my conclusion is, and I've lost room to write it down, but I'll just say it. My conclusion is that my original function, my f of x, this function, is increasing when x is out here or in here. So I could say that that my f of x is increasing from -infinity all the way up to 9/4. It does kind of smooth out here, but it never goes down. So I could make a case that I'm increasing from negative infinity all the way to 9/4, and then my function is decreasing from 9/4 to infinity. In number 3, my derivative is 8x cubed minus 24x, and I set that equal to 0 and solve, so I'll be able to factor out an 8x here, and that'll leave me with x squared minus 3. So this thing factors this way, which means that either x is 0 or x is plus or minus the square root of 3. So there's actually 3 values of x that make the derivative equal to 0. So I'll have negative square root of 3, 0, and positive square root of 3. And the square root of 3 is somewhere between 1.5 and 2. So those are my critical values, meaning those are the ones that could separate the sign change and the derivative. And so if I plot my sign chart, I'll find that I'll have negative values out here, which, so for example, negative 2 would be a value of x out in this area to check. I'll have positive values here. I'll have negative values here, and I'll have positive values here. So my original function is increasing only between these two numbers and out here to infinity. So f is increasing on the intervals minus square root of 3 to 0. These are intervals. And the interval square root of 3 to positive infinity. For number 4, the derivative is a little more complicated, so I'm going to give myself a little more room. It does use the quotient rule. And so I'll have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And that's all divided by the denominator squared. That's the same thing as in the numerator. If I simplify this, I'll have 7x squared here, and then I'm subtracting 14x squared here. So that's going to give me negative 7x squared. Then I also have plus 7 times 25, 175. Now the important thing about this is that since this is a fraction, remember we're trying to figure out where this is equal to 0. In all these other cases, we took our derivative and set it equal to 0, always setting our derivative equal to 0. So in this case, when we set this equal to 0, the only way for a fraction to be equal to 0 is if the numerator is 0. So, so the only way this can happen is if negative x squared plus 125 equals 0. Well, negative 7x squared plus 125 factors. It's negative 7, negative 7, x plus 5, x minus 5. So again, our polynomial factors, if you wanted to, you could clear the 7s, divide everything, so this is 175 here. Right up here. Anyway, 7 goes into both of these, obviously. You multiplied 7 times 25 up here to get 175, so obviously 175 is 7 times 25 down here. But the point is that this happens when x is 5 or negative 5. So on my sign chart, if I plot negative 5 and 5 as my critical values, then I can sample over here at like negative 6. I can sample it here at 0. That's always an easy number to plug in. Out here at 6. And so if I plug these into my derivative, remember I'm plugging them into this is my derivative formula. When x is 0, I'm going to have positive derivative. So through here, this will be positive. When x is 6, I'll have negative values. When x is negative 6, I'll also have negative values. So this function decreases from negative infinity out to negative 5. Then between negative 5 and 5, this function is going to be going up. And then from 5 to infinity, the function will be going down again. So it'll be decreasing. Finally, number 5, the derivative is a little bit weird looking. The derivative here is 2/3 times 2 minus x to the negative 1/3 times the derivative of the inside. It's the chain rule. But the derivative of the inside here is just negative 1. And so we end up with negative 2/3 2 minus x to the negative 1/3. This one raises the point about why, when we state our steps, we said that we want to find all the places where the derivative is 0 or undefined. This derivative is never 0. You could see that if you wrote it as a fraction. If we rewrite this negative exponent thing as a fraction, there'll be nothing in the numerator. It'll be 1 over 2 minus x to the 1/3. And so remember we said that the only way for a fraction to be 0 is if the numerator is 0. If you rewrite this as a fraction, the numerator is just going to be a number. It's not going to be 0. So this fraction can never be 0, but you can see that if x is 2, then we'll have 0 to the negative 1/3. Again, that's the same as dividing by 0. So that's bad. So that means that the derivative is undefined. So f prime of x here, let me just scroll down a little bit more. F prime of x here is never 0, but it is undefined at x equals 2. And so in our number line, we would just put 2 on there. That's a critical point. Sometimes you'll see people making this critical point an open circle instead of a closed circle to indicate that the function is actually undefined. There's nothing there as opposed to being 0. But it doesn't matter. We usually just think of it as a way of dividing our bins up. Anyway, so if I sample to both sides, I'll find that over here I have a negative derivative, and over here, and then over here I have a positive derivative. And so again, this function, the f of x function goes down until x is 2, and then it goes back up again. So in practice 2, it just wants you to go back. It's the same functions. It wants you to go back and identify relative maximum or minimum, meaning sort of low spots or high spots. And we can do that without really having to redo anything. Hopefully you have a better organized, you can organize this better in your notebook than I can on this slide. But I can go back and I can identify these places. Remember, this is a place where the function itself has stopped going up and started going down. So this, at x equals 0, the function is going to have a high point. The function has stopped going up and started going down. So at x equals 0, I'll have a relative maximum. If I want to know the y-coordinate of that relative maximum, I'll need to put 0, the x value, into this function. Remember, the function f of x is what tells you y-coordinates. So that'll give me the coordinates of the point that I know is a high point because the function has stopped going up and started going down. Similarly, the function stops going down and starts going up at x equals 2. So I would say that at x equals 2, I have a relative minimum. I can put 2 for x into this formula to find the y-coordinate. In number 2, at x equals 0, there's nothing going on. This is not a turning point. The graph went from increasing to increasing some more, so the graph did not turn over at this point. But at x equals 9/4, the graph of f of x does go from increasing to decreasing. So at 9/4, I'll have a relative maximum. In number 3, here I have a relative minimum because the graph has stopped going down and started going up. Here I have a relative maximum at x equals 0. Here I have a relative minimum at x equals the square root of 3. And again, to find those y-coordinates, I'd have to plug them back into this equation. In number 4, I have a low point, a relative minimum at x equals -5 because the graph of f of x has stopped going down, stopped having negative slopes and started having positive slopes. So I'll have a relative minimum at -5 and a relative maximum at x equals 5. And then finally in number 5, I only have one critical value at x equals 2, and we can see that the graph has stopped decreasing and started increasing, indicating that at x equals 2, I have a relative minimum. So the sign chart analysis allows us, this is called the first derivative test sometimes, but basically it's make a sign chart of the derivative and then see where the graph of f of x is increasing and decreasing, and then from that you can tell where you have these relative high points and relative low points.